we are going to cover roots of unity filter in this lecture. So the n complex roots of this equation, z power n minus 1 equal to 0, are called the nth roots of unity. You can see that they can be expressed as e power 2 pi I k upon n. This is called the Euler form, and where k ranges from 0 to n minus 1. Note that plugging in k and k plus n give the same value here. So as long as I and as long as j and k have different values modulo n, e power I 2 pi j by n and e power I 2 pi k by n will be different. Now, suppose 1, zeta 1, zeta 2 up to zeta n minus 1 are the nth root, are all the nth roots of unity. And suppose m is an integer not divisible by n, then this sum zeta n minus 1 whole power m plus zeta n minus 2 whole power m plus dot zeta 1 whole power m plus 1 is always 0. The proof is left as an exercise. And note that if m is divisible by n, then this becomes 1, this becomes 1, all of them become 1, and the sum is n. Now, nth root of unity is called a primitive nth root of unity if it isn't mth root of unity for any m less than n. So, for example, I is a primitive fourth root of unity, while minus 1 is also a fourth root of unity, as minus 1 whole power 4 equal to 1. But minus 1 is not primitive because it is also second root of unity. And note that whenever you put k equal to 1 in the Euler form, this e power 2 pi I by n is always primitive. Now, this is not functions, but when you consider the polynomial whose roots are the nth primitive roots of unity, that polynomial is called the nth cyclotomic polynomial, and beta of the polynomial is phi of n, where phi is the Euler phi function. Now, suppose that zeta is primitive nth root of unity, then show that zeta square dot up to zeta n minus 1 are all distinct. Now we show some applications. So we will be using this lemma a lot. Find summation 100 C3k. Of course, k ranges from 0 to 30. So, x equal to 1 plus x whole power 1000. We want to find sum of coefficients of now you plug in x as 1, then omega and omega square, and omega is a third root of unity. Note that this is a primitive root of unity, so all of these are distinct. Now, whatever the things, the exponents that were not divisible by 3, 1 power as n, 1 power n plus omega power n plus omega square power n would be 0 due to this lemma. And everything will be those with exponent divisible by 3. This sum is 3 times sum of 1000 C3k. So we need to find p plus omega plus p omega square upon 3. Now p1 is 1 plus 1 power 1000, that is 2 power 1000. 1 plus omega is minus omega square, and 1 plus omega square is minus omega. This should be omega. Now this becomes omega 2000, and this becomes omega power 1000. And if you know how to deal with nth roots of unity, you can write omega power 2000 as omega square, and this is omega, and they sum to minus 1. So we needed to find is 2 power 1000 minus 1 upon 3. This is an exercise. These are problems, so these are much harder than this exercise. In case you wanted to try that. Now, snake oiling. So, as they say, snake oil is the cure of everything. So, snake oiling, the name is famous because it solves almost every generating function related problem. Now, what is next? Before that, suppose we have double summation, that is summation equal to 1 to 2, summation equal to 1 to 3, f of ij, where f is some function. So what this means is you compute the summation first and then you compute the outer one. Now we will show that you can interchange the sigma signs and still keep s constant. So s is summation equal to 1 to 3. This will be f of I, f of 1 comma g and f of 2 comma g. Now this becomes f of 1 comma 1 plus f of 2 comma 1 plus f of 1 comma 2 plus f of 2 comma 2 and f of 1 comma 3 plus f of 2 comma 3. Change the order. So instead of summing this first, then this, and then this, you add use use sum by taking the first commands of every sum, and then taking the second summand. So this is f of 1 1 plus f of 1 2 plus f of 1 3 plus f of 2 1, f of 2 2, and f of 2 3, and you can see this is summation I equal to 1 to 2, summation j equal to 1 to 3, f of ij. Note that the sigma signs are interchanged, but that does not change the value of s. Now you can interchange them without thinking about the limits if these two variables do not depend on each other. In case they do, that is, suppose you have summation I equal to 1 to n, summation j equal to I to n. So here j depends on I. Then when you change the summations, the inner limits will get changed. So I was from 1 to n, here I is from 1 to j. And j was from I to n, j is from here from 1 to n. So whenever you are trying to switch some, you must take care of the upper limits of the sigmas. Now, how are we going to use this idea in generating functions? So, suppose the sequence that we want to find the generating function of, the terms of that sequence are themselves a sum. That is an equal to summation fmn, where m ranges from something to something. Now we try to find the generating function, that is a of x equal to summation n equal to 0 to infinity an x power n, and you switch the order of summation in hopes that this will be easier to compute than this sum. Let's try an example. So we have to evaluate the sum I equal to 0 to n minus I ci. Let's calculate a few starting values. So a of n denote this sum. A of 0 is, so I equal to 0 to 0. A of 0 is 0 c 0, which is 1. A of 1 would be, so n equal to 1 here. A of 1 would be 0 c1 plus 1 c0. This is 0, this is 1, so the sum is 1. A of a2 will be 0 c2 plus 1 c1 plus 2 c0. Again, this is 0, this is 1, and this is 1. The sum is 2. And if you calculate a few more values, you will get that they seem to be Fibonacci numbers. That is 1, 1, 2, 3, 5, 8, and so on. You can try putting an n plus 2 here and proving that an plus 2 is equal to an plus 1 plus an using some binomial coefficient identities, but we will be using generating functions here. So we want to calculate the generating function corresponding to the sequence an. That is, we want to calculate 1 plus 1x plus 2x plus 3x cube and so on. Imagine it like this. There is this is the same. There is a x multiplied here and a x multiplied here. There is a x square here, x multiplied here, x square multiplied here, and x square multiplied here. Now, instead of first summing like this horizontally and then adding them up, we try to do it diagonally. So there are two ways. One way is you add these things, is 0 c 0 plus 0c1x plus 0c2x square plus 0c3x cube and so on. You do that, and then this, that will be 1c0x plus 1c1x square plus 1c2x cube and so on. You go this way. Another direction is you go this way. So you do 0c0 plus 1c0x plus 2c0x square plus 3c0x cube and so on. Then 0c1x plus 1c1x square plus 2c1x cube and so on. Note that we are just changing the order of summation. We are not doing anything fancy here. So a of x will be written to 0. I n minus c x power n. And sums, you get summation I, summation n greater than equal to 0, n minus I c x power n. Take out an x power I from here. Summation I x power I. This sum. Now note that I is constant in this inner sum and n increases by 1 at each step. So the upper part of the binomial coefficient increases by 1 at each step while the lower part is constant. Remember identities from the first lecture. This infinite sum has part increasing by 1 at each step, lower part being constant. So the thing we are looking for are these type of where the is increasing by 1, or the upper part is constant and the lower part is increasing by 1 at each step. This. We have sum is equal to xy upon 1 minus x power I plus 1, and you multiply by x power I, multiply by I x power 2y upon 1 minus x power I plus 1. Now note that this is an infinite GP. Each term is multiplied by x square upon 1 minus x. So the formula for infinite GP, use the formula for GP, you get that ax into 1 by 1 minus x square. Now we leave it to the viewer to verify that this is in fact the n plus 1 Fibonacci number. So an is the n plus 1 Fibonacci number. Now notice that I have left the limits here, and it is left to the viewer to make sure limits don't cause any problems. To make sure that at each step the limit stays the same. Once you have completely digested this, try to evaluate this sum. That is here a constant in k, in this case c 2 power n minus k. Before ending the lecture, I would like to mention a few things. So this idea of changing the order of summation is helpful in integrals as well. That suppose you want to find an integral, let me give you an idea of how it happens. So suppose you want to find some integral. Suppose you want to find some integral. Suppose you want to find this some integral summation of x. What you do is you write this f of x as another integral, and then you have a double integral, and then twist the order of integrals. And most of the times, the second integral is easier to calculate than the starting one. And anything else? Okay. That's it for the intro to generative functions. If you want to read more, you can check out these sources. Most of the Most of the material here was taken from the first two books, that is Functionology by Herbert S. Wilf and Problems from the Book by Ito Andrescu and Gabriel Dosminescu. With that, I end the lecture and I wish you a good day.